Hello everyone, welcome. We are going to be talking about growth and decay, okay? So we're going to be applying what we learned about exponential functions and applying it to word problems. Let's go ahead and let's begin. Let's see right here. Boop. All right, so make sure you're following along our learning objective very officially here. I will identify the initial value common ratio domain and range of an exponential function. And apply it to real-world problems. Okay. And solve real-world problems. Kind of a long one, but there we go. All right, let's go ahead and fast forward. Now, other years we might do more, but because we are kind of on a timeline, let's go ahead and let's get right to it. We have an equation for exponential growth. Let's look at each component. The y is the total final amount. Okay, and so this right here, this is super duper important. Okay, y equals a times 1 plus r to the power of t. Let's go ahead and look at a. A is right up front, and this is our initial value. Right here, r is our rate of change, sometimes referred to as or common ratio. And then finally, we have t right here, and t is for time. Let's see if I can spell it. One thing I would make sure to remember is that whenever you're looking at what's inside the parentheses, if it is greater than 1, then you know you're dealing with growth. Okay, so let's look at this right here. Here we have our equation, y equals 25 times 1.13 to the power of t. And so you'll notice that what's inside the parentheses is bigger than 1. So we are dealing with growth. Let's go ahead and look at this. Example 1. The number of purchases in millions made on a website can be represented by the equation y equals 25 times 1.13 to the power of t, where t is the number of years after 2014. Okay, that looks probably important. We would like for you to interpret the parameters of the equation. All right, so the first thing we want to go ahead and do is, let's look at what else is important. Aha, this phrase right here is also very important. The number of purchases in millions made on a website. And when you see can be represented by, that's kind of getting an indication regarding what y is. Okay, so let's look at this. First of all, y. Y is the number of purchases, because the whole equation will tell us the number of purchases, the total number, in millions from the website. Then we have A, okay, and so remember our formula kind of look like this. A is what's in front of the parentheses. So here we have 25, right? So A is equal to 25, what? Well, that's our initial value, right? So that must be 25 million purchases. And so when did it all start? Well, it started in 2014. Okay, let's go ahead and look at R. R is 1 plus R. So now in order to find that, we can kind of set whatever's in here, right? We say 1.13 is going to be equal to 1 plus R. So we simply just solve for R. We subtract by 1, both sides, because that's our additive inverse. We have R is equal to 0.13. Okay, well, what does 13 actually mean? 0.13 is going to be our rate of change, our common ratio. Now remember, we could write it as this, or we could represent it as a percentage, where you move the decimal 2 times to the right, and you have 13%. Okay? And finally, T is for time. Now that is our unknown here. We don't know the time. And so this is T will actually represent, go ahead and write it here, the number of years. It actually tells you T, right? T is the number of years after 2014. Okay. All right, so those are all the parameters of the equation. Now, if we wanted to make a prediction about the future number of purchases made on the website, we could do this. We could say, let's put it in our calculator. And I'm going to type in the equation. So to put in an equation, we hit y equals, right? If we start right here, we're at y equals. And then we just type it in. Like I see a 25, I put it 25. I see a parentheses, I put parentheses. And 1.13, close parenthesis. Now, we know that the calculator is not a fan of any other variable except for x and y. So I hit my caret right here, and then I'm going to put an x in place of t. So I might make a little note like that, right? You know, hey, by the way, I set t equal to x, so I know. And then we're going to go to our table, second table. And if I was a consultant and I was trying to, use my numbers to basically deliver a powerful statement, I know X is T, right? That's the number of years. So that's like 10 years and 10 years this. And then Y is the number of purchases. So I'm looking for like a really good value. Ooh, okay, here, this is in millions, right? So I can say, oh, it's in excess of 100 million. That sounds like a good number, right? So we could say, let's use this point right here. Let's use the point 12,108.36. And again, this is 12 years after 2014. Okay. And so that means if I do the math, right, we're adding, that's 12 plus that, which is 2026. Yes? In 2026. So if they started the business, then I can say, look, by 2026, and then this right here, the Y value, that is the number of purchases in millions, right? Millions of purchases. So let me write like an actual statement here. If I was going to sell this, I would say, you know what? By 2026, by 2026, this website will have more than 100 million purchases. And that should be a statement that gets people's attention, right? It's like, what? So that's kind of the prediction I would make, right? go ahead and let's look over here. Example 2. Now, if you have any questions as we're going along, please bring them to my attention during sync, okay? So example 2, we have a population in 2013. The town of Flat, that probably looks important. I'm going to circle stuff that looks important. 2013, the town of Flat Creek has a population of about $280,000. 280,000. When they talk about population, they mean the number of people, right? So I know those two numbers are connected. And a growth rate of, that sounds important, 0.85% per year. Okay. We want to write an equation to represent the population of Flat Creek since 2013. Okay, a couple of things that are important there. Number 1, since 2013. That's probably an indication. That's going to help me understand my initial, right? And it'll be important for the other things. The other thing is we want an equation to represent the population of Flat Creek, right? So right there, this phrase, to write an equation that represents, this is basically telling you what y is. So let's go ahead and let's write all this stuff down. So I'm saying, okay, y is probably going to be the population of Flat Creek, right? That's a total amount, the pop of Flat Creek. Let me look at the other ones, right? We had y was the total amount. A was our initial value. Well, since it was since 2013, we know that's your initial, right? That's when we began. That's the first. So my initial value is probably going to be A is equal to 280,000 people. Okay. Now we have a rate of change, which they give to us in a percent, right? So we need to kind of keep that straight. So last time we had a percentage. We want to basically move it. We moved it. So let me kind of show you here. We have a percentage, a rate that is at 0.85%. Now, whenever you have decimals, if you start with the decimal and you're going to a percentage, you're moving to the right, okay? If you're going from the actual percentage to the decimal number, we would need to move to the left. So I'm going to start right here, and I'm going to move 1, 2, okay? So we're moving to the left. So what my number is going to end up being is 0. Because I got to put a little 0 in there, there's my decimal, 0085. Okay? Now, that's our rate. And then we can look at time. Time is our unknown variable, right? T is the number of years. Since 2013. Okay. So when we write our final equation, it's going to look like this. Y equals, and I'm going to put in my population because I know it, 280,000 times 1 plus, I'm going to put in my actual rate. We don't want the percentage in there. So that is 0.0085. And then to the power of t. We could write it like this, or we could actually write it like this. I'm going to add those two numbers, and I end up with 1.0085. Make sure my point is very distinct. To the power of t. And those are my answers. My favorite answer is probably this one right here. Now, according to the equation, what will be the population of Flat Creek in the year 2023? All right. So in the year 2023, I got to figure out since 2013, right? The word since 2013 basically means that I'm going to subtract 2013. That's how we're going to interpret that. So we're going to subtract 2013, and essentially we end up with 10. So it's been 10 years since 2013. Now, let's go ahead and let's put in that. We're going to go to y equals. A couple of different ways we could do this, right? Number one, if it's a nice integer, this is t, right? And last time, remember, the calculator doesn't like t, so we have to set like x equal to t, right? So if you'll notice on your table, all of the x's are typically these nice integers, right? So if you have a nice integer, you could definitely use your table. You could pop it in like so and just say, okay, I got 280,000 times 1.0085, close parenthesis to the power of x. Oops, put a little extra 2 there. Let me delete that. There we go. Always step to the side and make sure, does it look the way you want it to look? Yeah, I think it does. All right, so now I'm going to go to my table and I can actually look for 10. And guess what? There is my population, right? I have a population of, because when x is equal to 10, basically y is equal to 304,731 people. Okay, there is one other way you could do it where you simply just plug it in. And now this method would work no matter if you have 10 or they wanted to know 10.35 or whatever weird little number they had, it's gonna work. And so you just absolutely just plug it in, and instead of the t, you actually put in the value of 10, right? And so this is what it looks like. 280,000, make sure I got the right number of zeros, times 1.0085, close parentheses to the power of 10. I put a little caret. And now I hit enter, and I get the same exact answer. So my formal answer would be, in the year 2023, Flat Creek should have a population of 304,000. And you know what? I'm sorry, but that 0.29 of a person doesn't count. Sorry, not yet. So we're just going to round it. And we have our official answer. Okay. So that's growth, folks. Now, when it's decay, essentially we're looking at a number that's going to be smaller than 1, which makes sense because it's subtracting the rate, right? So same thing right here, right? This is going to be our total. This is going to be the total final amount. Here is our initial value. Here is going to be our rate of change. All of this is the same, right? Rate of change. And it could be also referred to as a common ratio. Okay. Let's see. So, and then finally, of course, this is still time. And the thing that I would keep in mind is that if you have a value inside of the parentheses that is less than 1, you know you are dealing with decay. Okay. Let's look at example 4. We have the percentage of people without a high school education in North County can be represented by this equation. Please interpret the parameters. Got it. Okay. So let me try and get just the equation here. I think one magical phrase is this right here. represented by the equation. That's telling me, hey, everything before refers to y. So y is the percentage of people without a high school education. Without a high school, that's a W, right? Without a high school education. So I'm abbreviating in order to fit it all in, right? We've got A. A sits right in front of that parenthesis, so it is 0.14. We want to make it a percentage. Usually a percentage number is going to look bigger, right? So we move it to the right. When we're going from decimal to percentage, we move it to the right. And so that ends up becoming a percentage of 14%. Okay. Then we have our value of R. R is our rate. So if we need to do that, we go with like 0.83. That's everything inside, right? And I know that's equal to 1 minus R. Okay, you could do this a couple of ways. I'm going to go ahead here and just subtract 1, I guess. Subtract 1. And I get, see, I don't want to mess this up. Negative 1 plus 0.83. So we get our negative 0.17 equals negative R. And we can just divide by negative or change all of our signs. So you get positive, positive. And R will now equal positive 0.17, right? If we're talking about this as a percentage, then, and the reason, like, with the last one, we had initial, right? We had initial value. Well, that was in millions, right? So our initial value here was 12. And so Y was the number of purchases. That was 25, right? So that was 25, and that had to do with Y, right? It was 25 million purchases. So we have to kind of consider that when we're talking about A. What is A referring to? Well, A here is basically the percentage of people without an high school education. So our initial A was 14% of the people with, it was actually of the population, right? Sorry. So it was 14 without the high school education. Let me try and make this up. Right. Our rate was 0.17. So if we move that 2 times to the right, we can get the percentage. And we're looking at 17%. We have a rate of 17% decay. Okay? Very important that we make a note that it is 17% drop. Decay are all common words. In the percentage of people without high school education. And then finally, T is for time, which we still don't really know. And does it tell us like years or seconds or minutes? No, it doesn't. So let's go ahead here. Make a prediction about the future education of the population of North County. So let's go right over here. We're going to clear that out, and we're going to put in our equation. Y equals, we got 0.14 parenthesis, 0.83 close parenthesis, to the power of, that's the caret, and then instead of T, we put in X. Okay, so I'm going to make a little note. I'm also representing T with X. I'm going to go here, second table, and I want to make a prediction about the future. All right, got it. So in general, kind of looks like we may have started off, let's go to the very first year, right? We start off with 14%, right? Because I'm just looking at those first 2 digits. And then whatever they're doing in the community, you have less and less uneducated students or an uneducated population, right? So as we go through here, let's just go, boom, by 10 years, you're looking at 2%, right? We can pick any number, but you know what I always think? Let's look for a number that looks dramatic. Let's look for one that drops it below 1%. Boom. Let's identify this point here. We've got 15 and 0.00856. Let's talk about what that means. 15 is X, and X is time. So this is 15 years since, let's see, does it have a since? Nope. It's just, you know what? Let's just make the assumption that they're talking about years because there's no indication. So we can just say 15 years. We know it's time for sure, right? So in 15, that's our time. And then this, if we want to rewrite it as a percentage, we again want to make it a little bigger. So we move it to the right. And we're looking at a percentage that looks like this, 0.056%. Now, just to be dramatic, I would probably, would you agree that 0.856% is a smaller number than 1%, right? Because you got like 0.8 and this is 1, right? So just for drama, I would say that in 15 years, North County will have less than 1% of their citizens without a high school education, which is a benefit to the community. Okay. Questions? All right. I don't know why I asked that, like somebody's going to respond. Okay, so let's go ahead. Let's look at example 5. But if you do have questions, please write them down. Okay. Let's start here with example 5, our last example, guys, and we are done. So here we have a charity. Again, we are in this section of decay, right? So we're definitely expecting for the numbers to go down. So, you know, they started off with a pretty high percentage of 14% last time. And then by the time 15 years have passed by, they were like less than 1%. So in this one, we have a charity. During an economic recession, a charitable organization found that its donations dropped by 1.1% per year. Before the recession, its donations were at $390,000. We want to write an equation to represent the charity's donations since the beginning of the recession. All right, let's look and see what probably looks important. Usually numbers are, right? And the fact that it says dropped, that's usually an indication that, hey, we're probably dealing with decay, right? We're going to subtract 1.1. Let's see, before the recession, the donations were this. That's probably like an initial amount, right? And let's see, right, represent. Okay, there's that magical phrase. We want something to represent. And so that's probably telling us like, represent the charity's donation since the beginning of the recession. That's probably telling us what Y is, right? So let's look at this. This is probably Y. This is probably an initial amount right here, and this probably has to do with the rate. Yes? So, a couple of things. Number one, we have, let's see, A is equal to that. R. We're going to have to change it, right? We don't put percentages in there. So, let's change that 1.1%. And now we're going from a big number to usually smaller when you take off the percentage. And let's move it to the left, 1, 2, and we put in a 0, right? So when I write that, R is actually going to be equal to 0.011. That's R. Okay. Here's A, and Y, we know what it is. So let's write our equation. Y is equal to, A goes in the front, times 1 minus that small number, and to the power of t. And we might have it this way, although we probably want to actually simplify. 1 minus 0.011, and we have y is equal to 39. Is it 39,000? No, it's 390,000. Hello, extra, 0. Times 0.989 to the power of t. So yay, there we go. There's our equation. Last thing, we're going to use that to estimate. You know what? This would be a great time to pause it, see if you can do it. I'm going to go ahead here. I know that I'm looking for 5 years. That's probably t, right? And it's a nice number, so I'm probably going to use the table. Let's clear it. 390,000. Do I have enough zeros? I do. Times 0.989. Close parenthesis to the power of, it doesn't like t, it likes x. Let's put that in. Second table. So let's keep in mind that t is also represented with x. I look for 5. There's 5. And there's my answer. So estimate the amount of donations 5 years after the start of the recession. We are looking at donations I approximate to be approximately exactly 369,000. And are we talking about dollars? We are, because y is, yeah. And let's see. Oh, maybe $17 too. You can say it like that. And there we go. Ladies and gentlemen, that is how we apply growth and decay exponential functions to real-world problems. Have a beautiful day. Bring all your questions to me in sync. Thank you.